Uh, Welcome to lecture number 3 on transformers. In the last lecture, we discussed about the construction of transformers. We actually only discussed about the construction of the core of the transformer. There are a number of other elements of a transformer that we'll be actually studying as this course progresses, and most of it you will cover in the design of electrical machine subject. So you have the transformer tank, you have cooling circuitry, you have calls relay, and other fins, fans, extra. So these are other components, the conservator, extra. So these components are also included in a transformer. I did not highlight these in the last session because we are only dealing with the core of the transformer in this course actually. In detail construction of the transformer, you'll study that in the design course. So coming back to we had actually started the ideal transformer. So we'll do the analysis of ideal transformer today. So some things we discussed already in the last session. As I said to you that for an ideal transformer, the equation Vp divided by Vs is equal to Np divided by Ns is known as the turns ratio A, and also it is equal to Is divided by Ip. Fine. So this is your transformer equation. Also regarding the power equation, if we look at the power equation of the transformer, the input power of this transformer can be given as Vp Ip into cos theta. Talking about the real power of the system, real power input is Vp Ip cos theta, and the output power will be equal to Vs Is cos theta. Now we know already Vs is equal to A times Vp, and Vs is equal to Vp divided by A, sorry, and Is is equal to A times Ip cos theta. So A and A goes, so this is Vp Ip cos theta. So that's actually the input power. So we have already pointed this thing out that in a transformer, the output power and the input power, they basically remain same. One more equation, the impedance equation of the transformer. We know impedance of a system is given by V divided by I, where V and I represent the voltage and the current. And for a transformer, we can say the input impedance Z in will be equal to Vp divided by Ip, and the output impedance is equal to Vs divided by I of S. Fine. So this output impedance Z out can therefore be written as, since Vs is equal to from this equation Vs is equal to A times Vp divided by A, and Is is equal to A into Ip. So this is therefore Vp divided by Ip A square, where Vp by Ip is what? The input impedance. So Z out actually represents the impedance of the secondary circuit is equal to Z in divided by A square, or you can simply say Zs is equal to Zp divided by A square, or Zp is equal to A square times Z of S. So this is known as the impedance ratio of the transformer. So these are your voltage equations, current equations, the power equation. Also, if this is the output, this is your real power, we can also write the reactive power Q in equal to Vp Ip sine theta, and Q out will be equal to Vs Is sine theta. Again, you substitute Vs equal to Vp divided by A and Is equal to A into Ip. So you will see that Q in will be equal to Q out, that is Vs Is sine theta. So Vp Ip sine theta will be equal to Vs Is sine theta. So if your real power, your reactive power on the primary side and the secondary side are same, therefore your uh, apparent power S will also be on the two sides, that will also be same. One more thing to note about transformers is the rating of the transformer is not given in watts. We do not say this transformer is 20 kilowatts. We usually use the term this transformer is 20 kVA. The reason behind uh, specifying the rating in terms of VA, that is apparent power, is because the load of the transformer is not known to us, and whether it will be a resistive load, a reactive load, so how much power it will draw from the system is not known to us. So instead of defining the uh, rating in watts or in vars, we define the rating of a transformer in volt amperes, so that because the because of the uncertainty of the unknown nature of your load on the transformer. So this is your uh, uh, ideal transformer equations. So you have to remember these equations. This is your equation number 1. This is equation number 2. P out is equal to Pn is equal to Vpip cos theta, or you can also say Vsis cos theta. Fine. So this is equation number 3. Similarly, Q in is equal to Vp sine theta is equal to Q out is equal to Vs sine theta. So this is for an ideal transformer. This is equation number 4 that you remember. Equation number 5 will be this. Zs will be equal to Zp divided by A square, or Zp is equal to A square times Z of S, where A is what? A is this term, Np divided by Ns. Np representing the number of turns of primary winding, Ns representing the number of turns of the secondary winding. So now using these equations, first of all, we'll do one numerical on ideal transformer. After that, we'll take up the real transformer. So you have been here given a diagram, and there are two circuits. One is without transformers and another one is with transformers. You have to basically analyze both the circuits. In the what we have been given to us, what has been given to us is this transformer. The voltage source is 480 volts. It's an AC voltage source. The line, transmission line, instead of using transmission line, we can simply say that this is an electrical circuit, and the line impedance is 0.18 ohms plus J 0.24, and the load here applied is 4 plus J3 ohms. Fine. So in your first circuit, no transformers are attached. So you have to find out the voltage at the load and also the losses in this circuit. And second time, transformer is being connected at both the source side as well as at the load side. And now we need to find out what will be the losses and the voltage in this transformer. Fine. So part A, how to solve this. The first one is quite simple. We need to find out the voltage, the load voltage across your impedance, that the across your impedance. So we can simply first of all find out the current in the circuit. So if I say the current in this circuit is I, and the source voltage is V, uh, the total current in the circuit will be equal to Z load plus Z of the line. Fine. This is your source voltage, this is your line current in the circuit. This will be equal to, Vs has been given to us, it is equal to 480 angle 0 degrees. Fine. So you need to have scientific calculators with you. While as the line impedance has been given to us, it is 0.18 ohms plus J 0.24 ohms. Fine. So this is your line impedance, and your load impedance is 3 plus 4 plus J 4 plus J3. So you can calculate this and you'll get you can directly solve it using a scientific calculator. So you will get 90.8 degrees angle minus 37.8. Fine. So these many amperes is the current flowing in this circuit. Now if this is the current flowing in the circuit, the voltage across the load, V out or V load, is equal to I into Z load. Fine. So I is given to us, it is 90.8 angle minus 37.8 into Z load is 4 plus J3. So again you can solve this and you'll find out this voltage will come out to be equal to 454 angle minus 0.9 degrees, these many volts. So this is your output voltage, this is your load voltage in the circuit. Now with this voltage, so we have calculated one thing, we have to find out V load, and second we have to calculate the losses in this circuit. So what will be the losses? That will be simply equal to I square into R of the line. We are calculating losses in the transmission line only. Fine. So I square is 90.8. This simple I square R losses, angle minus 37.8 degrees square into R of the line. We are calculating active power in the circuit. So what is R of the line? R of the line, resistance of this line is 0.18 ohms. 0.18 ohms. So you do not need to have impedance, you do not need to include this reactance term here. We do not need this while calculating I square R losses. We are only taking the term R, we are not taking Z of this line. So you can calculate this and you'll find out the line losses will be equal to 1484 watts. So this is your transmission line when you are generating the voltage. So I have told you that we use transformers to reduce the transmission line losses. So we'll actually see whether our transmission line losses will be reduced or not in this circuit. So far, for the normal transmission line configuration, if we are not using transformers, our losses in the circuit will be 1484 watts. Now we are in the B part of this numerical. Now we are including what we are doing, we are including the transformers on both the source as well as the line side. So accordingly, the voltage and the circuit will actually change. Since we are not actually studying the equivalent circuit of a transformer yet, and we do not need for the equivalent circuit of transformer for this case, what we are going to do is we will be analyzing this circuit now, that is your with transformers, and find out what will be the losses in this system. Fine. So your transformer number 1 is a step up transformer with the transformation ratio of 1:10. That means if your voltage was initially 480 volts. Your transmission line voltage at this secondary side will now be equal to 4800 volts. Fine. So that 4800 volts is now being impressed across the transmission line. So what will be the uh, uh, what will be the transmission line current then? That will also be changed accordingly. So if initially the current was 90.8, so it will be reduced now. Fine. We to do this, what we'll be going to do is we'll be going for impedance matching circuitry. Fine. So in the impedance matching circuitry, what we have already studied how to transform impedance. So we have that load circuit. Mm, this is our system now. So it has its own resistance or its own impedance, and then you have another transformer here, and you have a resistance here. Fine. So this voltage is 480, 480 angle 0 degrees. This impedance is this is 4 plus 3j. This is 0.1 plus 0.24j. Fine. So this is your circuit now. This is a 1:10 transformer, and this is a 10:1. This is a 10:1 transformer. So what we can do is we can use the impedance transformation that we have studied just. We saw that the equation for impedance transformation that we derived was Z of S is equal to A square uh, rather ZP divided by A square. Zs is equal to Zp divided by A square. So if we want to transform this uh, impedance to the primary side, to its primary, this is secondary of this transformer is 4 plus 3j. So we'll transform this to the primary side. What we have to do is we have to see Zp equal to, we have to divide Zp, we have to uh, we have to multiply Zp, we have to multiply Zs, this voltage, by A square to transform it to the primary side. So this circuit then will then become this transformer is as it is. We have 0.18, we have 0. J 0.24. Then you have a transformer that is having a transformation ratio of 10:1. That means A for this transformer is 10. A for this transformer is 0.1. That's actually 1 by 10. For this transformer, A is equal to 10. Therefore, when this impedance is transformed to the primary side impedance will be equal to Zs into A square. Zs, where A is equal to 10, so this becomes 100 into Zs. Zs is originally 4 plus 3j, so this becomes 400 plus 300j. This is impedance transformation. So when you are transforming the secondary side resistance or impedance to the primary side, multiply it with A square. We could have also transformed the primary side impedance to the secondary side. Primary side impedance was this quantity. If we assume that this transformer was not there, so this was our primary side impedance, we could have transformed this to the secondary side, but in that case we should have divided this by A square, not multiplied it by A square. So this is your first step. Now another step will be transforming this transformer now, reducing the first transformer now, that is this transformer, and finding out what will be its effect when we transform it when we transform this voltage. So we have a transmission line network here that we analyzed without first the transformers, and now we are actually analyzing it with transformers. So first, we cannot directly access the uh, current flowing in this circuit to make to find out what is the current flowing in this to find out the current in this circuit, in this complete circuit. What we need to do is transform this circuit first to a single line diagram. So for that, the secondary transformer that we had first we had here, the second transformer, we have eliminated it by transforming the load impedance to the uh, to, to this primary side by multiplying it with 100. So we are getting this. Now this is your total impedance. Again, this is your impedance on the secondary side of this transformer. So what we can say is, if the transformation ratio is now 0.1, this impedance when referred to the primary will become equal to 0.1 square times Zs. So for this case, for this transformer now, Zp, so if this is Zp2, Zs2, this will be Zp1 equal to a square Zs, and I will also write A2, this is A2, this is A2, this is A1. So this is A1 square times Zs1. Now Zs1, we already know what is Zs1, so when we transform it to Zp1, this will be equal to, the circuit we will get is, multiply this resistance 0.18 into a square for this case is 0.1 square, so this becomes 0.18 into 0.01, so that this will come out to be equal to 0.0018, and this impedance will be equal to J 0.0024. This is 400 and 300. This will go back to their original values 4 and 3J. So this is our voltage here, 480 angle 0. Now again we can find out the current I flowing in this circuit, then we can find out the load voltage, and then we can find out the I square R losses. So I for the circuit will now be equal to 480 angle 0 divided by 0.0018 plus J 0.0024 plus 4 plus 3J. So that comes out to be equal to 95.94 angle minus 36.88. Fine, so this is your current now flowing in the circuit. So V load will be equal to 95.94 angle minus 36.88 degrees. The current into this impedance, that is 4 plus 3J. So this load voltage, the output voltage, will therefore be equal to 479 479.7 angle minus 0.01 degrees volts. Fine, and the losses in the circuit, P losses, will be equal to I square R. I will now be equal to 95.94 into angle minus 36.88 square into R. R for this case is now 0.0018. So this will be equal to 16 6.7 watts. Fine. So this is your voltage, this is your power loss in this circuit. With transformers, without transformers, the power loss in the circuit was 1484 watts. So with transformers, you can see the line losses has been reduced to 16.7 watts only. So this is the advantage of using a transformer. We have these calculations were based actually upon the fact that we have taken this as an ideal transformer. The practical transformer would not have it. There would have been a little bit more losses as compared to this, but with a practical transformer, but it would still have significantly reduced the transmission line losses in this system. So now we'll take up the operation of a real transformer. Now talking about an real transformer. So the basis of operation of a transformer is the same, the Faraday's law that we have already studied. And as per the Faraday's law, we have already studied that the induced EMF will be equal to minus n d phi by dt, or in terms of the flux linkage, we can say that E induced is equal to d lambda by dt, where lambda actually represents the total flux linkage. That's actually the product of n and phi. Now, what happens in case of where lambda is flux linkage, and it is given by n into phi average. Fine. Now, why phi average? When we talk about a coil and flux flowing in this system, all the turns of the coil are not actually linked with the same amount of flux, but uh, it can so be that the central turn has more flux concentration, is linked with more flux, and the ends are linked with lesser amount of flux. Uh, but on an average, we can decide that if the average flux that cuts through this winding is phi average, therefore the induced EMF in this coil will be equal to d lambda by dt, or E induced is equal to n d phi average by dt. So phi average here basically represents the average flux that actually cuts through each and every winding, each and every turn of a transformer winding. Where and n represents the number of turns of this coil. Now, what does this flux phi average depend upon? If we apply a voltage Vp, let me show a transformer here now. Where Vp is the voltage applied to this transformer, and Np is the number of turns of this primary winding. Ns is the number of turns of the secondary winding, and Vs is the voltage that's available at the terminals of the secondary winding. Fine. So phi average, it has been seen, is equal to 1 by Np integral of Vp dt. So the average flux of the transformer that actually cuts through each and every turn of the winding of the primary winding is actually proportional to the integral of the primary voltage that's applied to this transformer. Now, the concept with real transformers is that what we studied in case of ideal transformers is that all of the flux gets linked with the windings of the transformer. But in case of real, but in case of a real transformer, all of this flux is not actually concentrated. All of the flux that's actually developed by VP is not uh, concentrated along each and every turn of the transformer. Some of the flux will be actually lost in the air, and therefore if phi average is equal to 1 by np phi pd, we can say the primary flux, this is actually the primary flux, will be consisting of two components. One, it will be consisting of the mutual uh, flux, and two, and secondly, it will be consisting of the leakage flux. So this is the primary flux, that is the flux that is actually developed in the primary winding. Uh, this will be equal to, that's actually generated by this voltage Vp. Fine, so this Vp basically produces flux in this machine equal to phi p. Now this phi p is not exactly linked with the primary winding. Only phi m component of this flux is linked with the primary winding. This phi m basically represents the mutual, uh, the component of mutual flux, and some of the flux is actually lost in the air, so therefore referred to as the leakage flux. This phi m will be the flux that will now be linked with between by that will be actually concentrated between both the windings NP as well as NS, that will be actually responsible for inducing voltage in the secondary winding as well. So therefore you'll see the secondary winding will have a similar component. Phi s will be equal to phi m plus phi ls, where phi m is the mutual flux component that is actually responsible for the useful work done in this system, while as phi lp is the leakage flux in the primary winding, phi ls is the leakage flux in the secondary winding. Uh, Having said this, uh, it will be only the mutual flux that will be responsible for inducing voltage at the two ends of the primary and the secondary winding. So therefore what we can see here is, so using Lenz's law now, we know this Vp, fine, and this E induced equation, or you can use this equation, fine. So using these two equations, we can say Vp is equal to Np d phi p divided by dt, but since uh, d phi p is divided into two components, so this will be equal to d phi m by dt plus np d phi l p by dt. Similarly, vs will be equal to ns d phi m by dt plus ns d phi ls by dt. So these are your voltage Vp and Vs. Now this voltage Np d phi m by dt and Ns d phi m by dt, if we represent them by Ep and Es, we can therefore see the relationship between Ep and Es will be Ep divided by Es is equal to Np divided by Ns. Now what is these two voltage? These two voltage will be the voltage that will be available at the ends of these two windings. That is actually responsible for this mutual flux being linked between the primary winding and the secondary winding. So EP is the voltage at the end of the primary winding. ES is the voltage that's at the end of the secondary winding. While as VP is the voltage that's applied to the primary winding, but some of this VP is responsible for production of phi p, but all the phi p, the flux that is being produced by VP, all of that is not you put to useful work. Some of that is actually lost in the system. Only phi m component of that voltage of that flux will be linking the primary and the secondary winding and resulting in energy transfer from primary to secondary winding. So in between the application part and the available part, some of the voltage is actually lost, and that voltage is needs to be corrected. That voltage needs to be actually taken care of. Uh, Not taken care of. That voltage is actually lost in this system, and because of which we need to realize that a real transformer is actually different from that of an ideal transformer. Fine. So Vp is the applied voltage on the primary winding. It produces flux phi p. Although this phi p is not linked between the primary and the secondary windings, this phi p is not basically linking the primary and the secondary winding. Only some portion of phi p is linking the primary and the secondary winding, and that portion is equal to phi m, the mutual flux, because of which the mutual inductance component is actually between these two windings is responsible for production of. What happens in a real transformer? Vp produces flux phi p. Some of this flux is lost in the air. Only the flux, so this phi p, some of the flux is lost in the air. That is actually equal to phi lp, the leakage flux, and the mutual flux is actually the component of flux that links the primary winding and the secondary winding. So phi m is actually responsible for production of voltage at the uh, end of this secondary winding. Now this phi m that's actually linking the secondary coil will actually result in production of its own. That actually it will be responsible for production of flux on the secondary side as well. So phi s, the total average secondary flux uh, will be equal to phi m plus some. Now there will be some leakage associated with the secondary coil as well, because of which there will be again a drop in voltage, and the final voltage that will be available here will be equal to Vs. So Vp is equal to Ep plus Np d phi L by, this will be the drop in voltage because of the leakage flux component, and Vs will be equal to Es plus Els. This will be the drop in voltage because of the secondary leakage in the secondary flux, uh, secondary winding, leakage flux associated with the secondary winding. So you have two uh, drops, two voltage drops. One is ELP, the the voltage drop because of the flux leakage in the primary winding, and then you have ELS, the voltage drop because of the flux leakage in the secondary winding. So VP and VS, uh, what was the case in case of an ideal transformer was VP divided by VS was equal to A. That was NP divided by NS. But in case of a practical transformer, VP divided by VS will not now be equal to A because of the drop in the primary winding ELP and drop in the secondary winding ELS. But the mutual flux component that will be responsible for production of voltage at the ends of the windings EP and ES, they will follow this. Uh, uh, they will actually follow this transformation ratio. That transformation ratio EP divided by ES will be equal to NP divided by NS. So this transformation ratio is now limited to the ends of the primary and the secondary winding only. But at the terminals of the primary winding and the secondary winding, the voltage will be different. So VP is not equal to EP and ES is not equal to VS in case of a real transformer. So VP divided by VS will not be equal to NP divided by NS in case of a real transformer. It will be EP and ES that will follow this rule. Uh, So this is the basics of a real transformer. Now we need to go for a detailed analysis of this real transformer, wherein we can see actually how the magnetization curve results in the how we can actually model this leakage flux components in the both the primary windings and the secondary windings, also as how the flux actually varies in the transformer, whether it is sinusoidal or not, what will be the magnetization curve in case of a transformer. We need to see that. We'll do that in the next session.